Today we're going to talk about the capacitor, how it behaves in DC and how it behaves in AC. So let's start with DC. So here I have a circuit in LT Spice. Here my voltage source is a pulse, but it's just going from 0 to 10 and stays there, so it's basically a DC voltage source. I have a resistor 1 ohm and I have a capacitor 100 microfarads. So let's run this thing. Okay, so let's look at the voltage of the pulse. So as I said, 0, and after 10 milliseconds you go 10 volts and you stay there. So now what is the voltage at the positive plate of the capacitor? Right there. Yeah, so it kind of follows the voltage of the pulse, except that here you have some charging going on. So it's pretty fast charging, but you can kind of see it. So green is the pulse and the blue is the voltage at this plate, the positive plate. So it goes from 0 to 10 and it stays there. And let's have a look at the current. Yeah, let me get rid of this trace and that trace. So here you can see that it goes from 0 amps, it goes straight up to 10 amps, and then it's going back down to 0, which is expected. Okay, so you have the voltage that goes like this and the current that goes the opposite, going down the opposite direction. So that's in every textbook. So that's good. So now let's see what happens when you go from DC to AC. So let's get out of here. Let's load the next one, which is this one. So this is a single pulse. Everything else is unchanged. This is a single pulse. Let's run it. So this is the pulse. Okay, 0, and at 10 milliseconds you have a pulse that goes to 10 volts and it stays there for 1 milliseconds and then it goes back down to 0. So yeah, so let's look at the voltage at this plate. So you go from 0 to 10 and back down to 0. Okay, so you can see that here you have some charging going on, and here you see some discharging. But the idea is that it goes from 0 to 10 back down to 0. And if the capacitor was 10 microfarads instead of 100, you would see no difference between the blue and the green. The green being this voltage and the blue being that voltage. But what's important to look at is the current through the capacitor. So let's look at that. And this is pretty cool because let me get rid of the traces, the voltage traces, distracting. So it goes from 0 amp to 10 amp, and then it goes back to 0, so some kind of discharging, and then this is what's cool about it. Now it's reversing direction, so now it goes to minus 10 amps and then goes back to 0. So you have a reversal of current. And if you want, we can I mean, this is considered AC, but let's look at the train pulse. Let's look at the train pulse. So it's the same thing, except that it's a bunch of pulses. So let's run it. Let's look at the voltage. So that's your pulse train. Everything else is the same. So you can look at the voltage here. And here you can see the same thing as in the single pulse, you can see it goes from 0 to 10, back to 0 to 10, back to 0. You see some charging going on and some discharging going on. And if you want, you can look at the current and you see the same thing. So what's interesting about it is this reversal of current direction. I think it's pretty cool. And I think the best way to explain this phenomenon is to consider a water analogy. So instead of seeing your capacitor as a capacitor, you kind of think of it as a horizontal, let's say on a horizontal pipe where there is water inside. So you have you're gonna have a left side and you're gonna have a right side. Again, it's horizontal, and in the middle you're gonna have a rubber membrane or rubber diaphragm in the transversal direction. When you have a voltage on the left side, what happens is that the water is gonna basically move from the left to the right, and it's gonna create some pressure on that rubber membrane. So it's going to push that rubber membrane towards the right. And the water on the right side of the pipe is going to be pushed towards the right. So if you look at it from afar, it looks like the water is just going from left to right. You don't even see that there is a membrane because all you can see is that you have a movement of water, even though the water doesn't mix between the left and the right side because of that diaphragm. So that explains basically the current going through the capacitor. That gives you a current in one direction, the positive direction. Now, let's say that the pressure stops. The pressure goes to zero. So now what's going to happen is that the elasticity of that membrane is going to push the water the other way. So it's going to push from right to left, or pull if you prefer. And that's going to create a reversal of direction of the water. So that's a way to see it, if you will. But in practice, I think you should just consider the capacitor as a black box and not try to understand what's happening at the atomic level. But if you really want to know more about it, I think this was discovered, that behavior was discovered by Maxwell, and he called that phenomenon displacement current. As you probably know, the electrons cannot go through the capacitor, just like the water cannot go through that rubber diaphragm. But when you look at it at the macro scale, it looks as if the electrons are going through. It looks as if the water is going through that rubber diaphragm. I'm going to stop here and I'll see you around. Bye.